as you want. Thank you.
So thank you so much, Professor Mangaram. It's a great pleasure. Thank you so much for your kind invitation and introduction. So we'll try to cover what Professor Mangaram mentioned as much as we could. Usually we'll keep time for Q&As during the last part of the session, but if you have any questions, also feel free to stop me. My name is Mohammed Zidan. I'm from MemryX. Currently, I'm leading the software and the architecture effort, and I'm part of the founding team at MemryX. I joined after finishing my postdoctoral fellow at the University of Michigan. So let's start, everyone. So just a very highlight about MemryX. We are a semiconductor company. We build software and hardware for accelerating edge AI. And our headquarters is in Ann Arbor, and we have several sites in Taiwan, India, Saudi Arabia, and our executive team is also based in California. We build our hardware and software ground up. We don't rely on third-party compilers. We don't rely on ready-made CPUs, and we'll try to click a little bit deeper about that. And our architecture is data flow architecture, which is the focus of the talk today. We provide the highest TOPS efficiency without the need of model retraining and tuning. And I'll touch base on that as well, especially for TinyML. There are a lot of use cases for our chips and solutions from VMS, robotics, agriculture, automotive, like you can't. And we have very related deployments. We can touch base on it as well. So our journey, we started in 2019, and our earlier chips were RAM-based because it does make sense to save power and area and everything. However, the RAM technology were not mature enough for market deployment at that point of the time. And we believe that we have good solutions. So for our product, which is already commercially available, we switched it to SRAM. However, we stayed faithful to the cutting-edge memory technologies, and our next product is planned to have 3D memories, and we call it XRAM. Right now, we have several R&D explorations for the best memory technology to use, and we can also cover it a little bit. AI memories does matter, and of course, you know that through your course, we'll cover it also a little bit. Since we have our product, this year we won the Edge AI Accelerator of the Year through the Edge AI Alliance, which is an independent alliance that, like the previous winners were Qualcomm and other big companies, and this was a great honor for MemryX. And also we have very good community reception for our software and hardware. Before we dig deeper, let's just show you, touch base how much performance advantage and power advantage we offer just using one of our modules. And you can have PCIe cores or multiple modules, just using one of our modules running at medium power, not at high power. So let's take the NVIDIA Jetson Orin AGX, which they're top of the line, and they claim tons of TOPS as well. So what we are running here is something called YOLO Pinch. It's 700 YOLO models, and we didn't optimize any of them. Each one of them is compiled and deployed out of the box. And each blue dot is one YOLO model. The x-axis is the FPS on AGX through TensorRT, through the optimized flow they offer. And the y-axis is the FPS on one M.2 module, just running for this one at medium power at 14 TOPS. That's it. Any questions, sorry?
No, I was just telling them the y-axis is your product.
Yes, sir. So the y-axis is the MemryX product. And if you look at the Jetson Orin, for example, we offer at a fraction of the top 6x speed advantage, 4x power advantage. And the 10 watt here is the whole module, whole accelerator, not just, some would report just the accelerating unit or even the array only. Here it's end-to-end power for the module versus 40 watt. And then you are more than an order of magnitude performance per watt advantage here. And you have a lot of power for actually getting more performance. How about smaller systems, edge systems that can run onto 1 or 2 watt or even fraction? We'll cover it later. So an edge AI module can be very efficient if built for AI and can outperform GPUs or classical compute systems like Jetson and the same. And again, I want to reiterate here, if we hand-tune or prune or optimize the models, we'll get even way more advantage. But here we were out of the box comparing apples to apples at similar latency. So this is the intro about MemryX. Before digging into the more academic related content, we'd like to show you industrial side of it. So at the end, you need something to be successful. When you publish a paper, your reviewers are your judges. And it need to be innovative concept, need to be like introducing something new to the science, but doesn't mean by fact it's a good product. But as an engineer, when you go to the industry, you need to build something that's sellable. And Professor Mangaram can also add his insight here because he has very successful like story here. So having something for research is one thing, and having a product is the real judgment here. So I would like to show you, we have a chip that is 60 flops, and I'll highlight why we call it 60 flops. This is one chip, one tiny chip. The M.2 module, and I can show you one of the modules here. This is the module with the heatsink. It's a tiny thing, even with the heatsink, can have 4 chips and can run up to 24 tops. Actually, the one we showed earlier, the benchmark, was just at 14 tops, not even 24. And we have also upcoming products, PCIe cards that can achieve 100 T-flops, and dense servers that can achieve 500 T-flops. That being said, T-flops is sometimes could be, or flops could be a hollow metric. What matters is how much performance you can achieve, how efficient you are. So it's not really apples to apples. And we have also third-party companies that actually took our tiny chip and start building modules based on it. And there are several of them. Like one of them want to claim the smallest inference AI box, like it's tiny, it's in Taiwan. Some of them are integrating them in an SLR CAM. We cannot disclose the name yet, but it should be a product at some point soon. Some of them are building tiny modules to be included in drones for safety, or like modules that for Industry 4.0, and so on and so forth. So we are enabling not only faster than GPU and Jetsons, we are enabling form factors and on the edge that cannot really use a GPU. You cannot put a GPU on an SLR CAM or a Jetson, but I can offer you similar performance with 1 or 2 of my chips. And then when you go to a tiny box with 1 chip, there where TinyML plays a big role. And I'll touch base into that as well. Also, it's great for Industry 4.0 and edge boxes. So I thought it's relevant to show it here. We have several companies building boxes based on the MemryX solution. And Industry 4.0 might be a little bit different than a one-chip tiny inference box or an SLR CAM or a drone, because you have plugged in a wall, you have more power, you can have 4 chips easily, or even like 8 or 16. but you cannot have a GPU because the IP rating requires passive cooling, requires dust and water resistance, everything you might consider. So you are now enabling another form factor that a GPU or like a classical compute cannot have. And this is just an example. Software, ecosystems, VMS is a longer story, but I thought it's worth highlighting that once you build a product, you start first by enabling use cases on the edge that others cannot. And then you also go to use cases that you are outperforming a GPU. Still, you can have a GPU. So I started by two cases that actually a GPU or a classical compute might not even fit here. So here is the highlight of the hardware product. I didn't mention the software or software stacks we're integrating in or whatever yet. Now I'll go to the core concept. How is this possible? And the answer here is MemryX data flow. But let me pause here for a second and see if any questions or any clarifications before digging deeper into the technical part of it.
Ask questions, however basic they are. What is IPA rating? Why do you need that?
Oh, for factories, actually, I'm not sure why it's a requirement, but it's a requirement in factories that you cannot allow dust, you cannot allow humidity to go in. And actually, one of our partners who, is currently working with one of the big 3 car manufacturers in Detroit, and for their assembly lines, they have a strict requirement. It needs to be passive cooling. It needs to be IP rated. Of course, there is a justification for it, but to be honest, I'm not into the process to know the justification. But we are enabling something that a GPU cannot enable because even a Jetson box will be actively cooled and cannot run there.
This is a really basic question, but how long does the development of one of your components take, like the entire site?
So our product, the latest product currently, that's the MX3 is in production for I think 10 months right now. We are in production since 2024. And then when you're talking about production cycle, there are 2 aspects for it. There is the design, and designing a new chip usually it's a couple of years. Big companies will say 18 months, but for a startup and for cutting edge technologies and whatever, it's a couple of years. But then once you are in production, from production to achieving revenue to building all the missing software stack for integration, whatever, it's also taking extra time. So and this is something we learned while we are in the field. If you're in the PC industry or a mobile phone industry where all the stacks are defined, from production to achieving very high revenue is 9 months. For the IoT and edge is usually 18 months because the software stacks are not well defined. You build your SDK, but you work with a VMS provider and they have separate APIs and they need you to integrate in a separate way. So having the chip and the initial software, usually for well-defined stacks is the whole production cycle. For IoT, this is just the start, and then you usually spend 1 more year adding more plugins and software layers to enable the IoT domain.
How many engineers does it take to design the MX2 to MX3, and how many were working on the chip design, circuitry, architecture, and then the software support?
This is a great question. So, and this is the major difference between a startup and a big company. So currently the whole startup, we are around 40-something engineers. And the 40-something engineers are actually doing the architecture, the software, the front-end design. We outsource the back end because of the license of the tools and whatever. But here is a point. We wear a lot of hats. If you are in a big company, you would be laser focused on, oh, you are designing ISA. And that's your goal. Keep designing ISA for the rest of your life or the next 10 years. on my team. No, you'll be designing ISA. And while you're not designing ISA, you'll be designing the macro architecture. And while you are not, you will work on the compiler graph engine. So we wear a lot of hats, and we need to move fast and very efficient. So yeah, it's and we rely a lot on automation. I can also highlight this. Automation is our superpower as well here. Otherwise, you cannot pull all this with just 40-something engineer. And actually 40-something including sales and marketing and the whole startup.
But yes,
Yeah, so specifically for the chip industry, it's one of rapid technological change. So the latest chip right now will probably be obsolete maybe 2 years from now. So how do you design chips in advance to anticipate the possibilities of competitors designing chips which currently are not out yet?
This is the like $1 million question. How to design ISA and chip that actually will survive the next generation. It's not only that the semiconductor industry is moving fast, it's also the AI industry is moving extremely fast. So how do you make sure that your chip will survive the new wave of AI models or AI generation? There are multiple answers to this. You need to balance flexibility of your chip while you still be efficient, because if you end up building a CPU or a GPU, then you'll be as efficient as a CPU and GPU, but NVIDIA will execute it better than you. So as a startup, we have to follow a different path. We have to take risk, but still with balancing of flexibility and efficiency. That being said, also we have access to newer technology that usually we are the first users to it. Big companies will not take that risk. Like when I mentioned here 3D memories, or when we were talking about RAM, this also gave us an advantage. Maybe their R&D teams are using it, but it will be in our products as well. The third thing, we build something from ground up. We don't recycle, like if you're Intel or NVIDIA, you're recycling what you have and optimize it for AI. We build something built for AI, which is giving us an architectural advantage over competition as well. Thank you for the great questions, folks. Let me move forward now and tell you about data flow. So as you for sure know, AI is a completely different workload, either generative, either conf-based, transformer-based. You count, it doesn't matter. It's not your classical program. It's a new wave of compute. And it's oversimplified here, but AI is a repetitive math over huge data. So why it does matter? You know how you have instruction fetch and data fetch? Your instruction fetch to data or program to data ratio is near zero. If you look at the model and start analyzing either generative or vision or whatever, your instruction to data is near zero because you keep repeating the same instruction on huge amount of data. So that matters because for traditional computing, we all know we have the von Neumann bottleneck, and memory bottleneck is a huge deal. And if you're using classical computing, actually typical analysis, instruction fetch and data fetch are 50% from your fetch. So we decided early on, we are building something ground up for AI. We are building near memory compute or immersed in memory compute. We are building data flow, no instruction fetch. We are building decentralized control, and I'll highlight each one of these later, through data flow execution, through memory communication, and most importantly, inherently modular and scalable. So this is the architectural advantage or the data flow advantage we are talking about. Let's dig a little bit deeper. I'll try to take it one step at a time. And if something is not clear, please stop me. So as we just mentioned earlier, it's a repetitive math. So you have a computational graph, actually. Like whatever you are accelerating, it's a computational graph, which is a perfect fit for data flow. So here is a simplified neural network, whatever the neural network is doing. you can represent it as a graph, and you get your data. It goes through the first node of your graph, you generate output, and then it flows through your graph or your network, and then you get output. Here it's a simple feed-forward network with just a couple of branches. So perfectly aligning with what data flow can offer. So if you can map each of these nodes to compute elements, and in that case, we call it here for simplicity MemryX compute elements. So the first node will be computed by 4 compute elements, and then the results will be passed to the next node, third node. So you are actually recreating the graph, software defining your chip to work as the graph. And each node of the graph will have different computational requirements, might require more cores or less cores. And this also will be translated into your data flow here. Any questions, sorry? Okay, so let me move forward. So this is just like scratching the surface. Data flow is the right way to go. So what we introduced here is what we call a tower architecture. So we are doing near memory or immersed in memory compute. And this is actually a simplified layout for how our chips are working. We have core groups, and core groups are a heterogeneous core. You can consider it as equivalent to the GPU multiprocessor, but not exactly. You have several what we call M cores and A cores. We can go to it later. And we have also lookup tables. We have shared weight memory. And each core group is a unit that you can replicate. And you have several core groups per tower. And then we have the feature map memory, which is your activations, for example, is acting as your communication fabric. You don't need a network on chip. And if each of these cores are data flow and you are communicating through memory, we can introduce something that kind of rare, which is true data flow computation. This also will allow us to have flexible design, because as long as I don't have centralized control, I have autonomous cores, just data-driven. So each core can work independently. So I can actually have a single chip solution that can run more power efficient for an edge solution just on a drone, for example. Or I can cascade these chips and have a larger logical chip that the host or the user, actually it's transparent because it's data flow, it's decentralized control. Data will go from the first chip to next chip as if they are one bigger chip. Compiler will handle this and we'll dig a little bit deeper about it. And then it's a larger logical chip. And in that case, it's a 4-chip M.2, or you go for 16-chip PCIe or whatever you want. And also you can have different form factors. And we have, I'll also show you how we are designing in a systematic way our architecture. Going from one single chip to a larger or smaller single chip or a combined multi-chip is a matter of market need, a matter of choice. It's not only working for this form factor, which also opens a lot of doors. Like you can go for sub-watt or a few hundred milliwatts run if you want, and really rely on the TinyML models and pruning and all these techniques. Or you can go to like actually edge servers if you want. So how is this possible? Usually, just to pause here, when we talk to our customers, we never mention that. They don't care about that. They care about what's your performance, what's your ease of use. But from an academic perspective, I think it also matters to show you how we can actually achieve what we highlighted earlier. What is the flow? What are the steps we did here? So usually we follow 4 steps when designing our architecture. We have our architectural concepts and mathematical modeling, and I'll show these steps. And then we build something called architecture tool. Then we go for detailed modeling and functional compiler, and then we go to the microarchitectural design. Any of our architecture goes into these 4 steps. So let's go through this flow chart, and I'll try to highlight it for you. So when you build a new chip, we know the last generation challenges. And you know it once you start working with customers, once you start deploying it. If you know it earlier, you would fix it, but nothing is perfect. So you know your last generation challenges, you know your next generation expectations, and you have an initial set of architectural features. So this initial set of architectural features are the concept of the new architecture. And we showed an oversimplified version of it earlier with the core groups and through memory communication. Then you take these initial features of architecture, and what we built is what we call architecture tool. It's an analytical tool we built in-house that's made up of literally hundreds of equations. And then these hundreds of equations are representing the first and sometimes the second order modeling of the architectural concepts. And it's solving it symbolically, and you need to have constraints for solving these equations. So we have the target specs. Our target market will require 50 TOPS for the next chip. Then this is my constraint. My area should be within this, so that's the allowed area. And you have all the technology and market constraints. And also we have the target models, and it's not the current models, it's the models that are upcoming, the research models, all of them. And then we have APIs tools that will consume hundreds of models, analyze them, and convert them into also constraints for the architecture tool. We have an initial ISA. And again, the models are customer guided and trending models. And then you will go and try to find a design point for your architecture. So for example, our current chip, each one small chiplet has 192 cores. So it's not a typical selection of the number of cores. Why 192, not 128 or 256? Because we take efficiency very seriously. So in that case, the architecture tool will try to solve it. It will not be able to solve it. Like usually you have to return to the drawing board, tune your specs, add new concepts to the architecture. And usually at MemryX, we know that if it's an easy problem, anyone can do it. We love challenging problems. So it's challenging, we go and return. And once we have a couple of solutions for our architecture, we don't go to the macro architecture and starting the front end. We cannot afford having a less efficient chip. We can only build the best efficient chip possible. So we take this design point and we build an end-to-end system C model that's bit accurate, timing accurate compared to the chip are within 10 and 20%. And it can consume actual compiled binaries. So it's a full-fledged system C simulator. And at the same time, we build the compiler. And the compiler will start consuming the target models and will deploy them to the simulator. We'll measure the performance, accuracy, and not overcomplicate the figure. Several of them will fail here. And you have to return to the architecture tool, refine the design point, and some of them you need to return to the actual architectural concepts. Once we are within our goals with a very small margin, we go to the macro architecture and build the front end and everything. Now the compiler design will continue for the next 2 years. This is the start, but we want to squeeze each and every bit of performance from our architecture. So this is how we are designing our architecture, and each and every choice I'll cover later was based on these systematic tools and approaches. So first choice we had, and let me just pause. How long I have for the lecture? Sorry, I missed this part. So I can only cover within the time.
That's time. If you have any questions, so this is going over how you would actually design not just the chip, but also compiler. Yes, questions.
I don't know if you already covered this, but like in the previous slide, you talked about how like customers like can also guide like the architecture. Like how do you balance between like specifically what kind of like design the customers want in regards and like general like AI just kind of.
So usually customers are not deeply technical when it comes to the architecture. Their guidance were like, I actually need these models at that amount of FPS. I need to run like 5 concurrent models, and each one is providing this FPS. So it's more of constraints than guiding the architecture itself. And you need to make sure that the customer required constraints can be easily achieved. But like they really don't understand below the compiler layer or the runtime layer.
Yeah, so it's ensuring like in 2022, you can meet their requirements, but also figure out what they would want in 2026 by the time the chip is in the market. Next
So
one.
this is a very good question. If you are working with big companies, they have vision and directions for their next 5 years, and they can tell you what you are expecting. Smaller customers are like, will tell you what they need today, and then you need to extrapolate as well. So this is a factor, but to be honest, with rapidly moving technology and rapidly moving field, you have to do a lot of guesses, and you have to rely on the technology trend more than customer guided. We hope it's fully customer guided, because when you build a chip, you know that already someone will purchase all the chips you are building. But for the AI field and edge field, it's not really the truth.
A few slides back, you mentioned that like the computational graph guides like the chip design. Does it change for like different types of neural networks, or is it more like a general chip?
Oh, so how we convert the computational graph into, so it's software defined. We don't design a chip for a given computational graph, and this I'll cover later.
Thank you.
Thank you. So let me try to move a little bit faster. One of the core differentiations in our architecture was technology driven, that we have separate memories for weights or parameters and feature map. Because initially we designed the architecture for RRAM, and if you get exposed to RRAM before, it's fast to read, very slow to write. And parameters are typically read-only, unless you are changing the model or swapping a new model. We are inference chip, we are not doing training, so parameters are read-only. And then feature map is the intermediate data, it's dynamic, it's read and write, so it's usually SRAM. So that was a technology driven, but actually turned out to be the best choice, even if we are using SRAM for weights and feature map, because we can now optimize the memory bottleneck for each type of data differently. The other thing, we don't build like a scratch pad or cache. We are distributed, truly distributed, immersed in memory compute or near memory compute, where we can get lowest latency, lowest power consumption, and the highest bandwidth. So this is one of the major features of the architecture. I'll just do mix and match of the features, and then they will come together as a bigger picture later. As we highlighted before, we are no instruction fetch. The core will run autonomously based on the data. And here is like, again, an oversimplified version of the 2 cores in the current chip. The M core, which is the Mac core, that's doing the heavy lifting. It has an array of Mac units, and it has data fetch, no instruction fetch. You program it once, it's keep doing this forever, and write back. Internally, it's also a data flow. So the whole architecture is data flow, and the core itself is data flow. And it has no knock. It can communicate with adjacent cores, can read from the weight memory, can read and write to adjacent F memory. Make it simple, make it very predictable. So when our simulator predict a performance is very accurate, but also when you run that chip, you don't get different performance or like jittery performance. It's almost always the same performance. But it also poses a challenge that I'll cover later, a real data flow challenge. And we have the arithmetic core that actually will run everything else other than the heavy lifting. We'll access lookup tables, we'll have a full-fledged ALU. Still, it's a data flow core. It has more instruction buffer, because of course, here you run more complex instructions. Now, if you have these cores and you have these distributed memories, let me give you just a taste of one of the equations in the architecture design when we talk about hundreds of equations here. So we need to derive the maximum value per core. We need to be very efficient. And is data flow, it's enabling us to do so. But as an engineer, there are always trade-offs. There is not a free lunch in engineering. So I'm just giving you here one trade-off. We have weights memory or parameters memory and feature map memory. You will never get enough bandwidth for your compute. You have to do reuse. No way around it. You have to reuse the data you are reading. The question, how much reuse you do? So if we have a large, bulky core, you can reuse the feature map a lot, but then you'll end up not having enough bandwidth for the weight memory because the reuse is low. And then if you have tiny cores, you will end up using the weight memory a lot for our architecture because you can actually get the weight memory data from your adjacent core, but you'll end up hitting the feature map memory bandwidth. So you need to find the sweet spot that actually will balance the feature map bandwidth and the weight bandwidth and the right core, what I'd say, granularity. That's why you saw that with even running at 14 TFLOPS, our accelerator can 6x be faster than a Jetson running at 100 TOPS, for example. I don't recall the exact number, but it might be 80 or 100. So how is that possible? Because it's built for AI. It's built to be efficient. And that will make it efficient on the edge for TinyML and so on and so forth. Now, the next challenge here is actually how you can enable data flow, how you could be truly data-driven. And here we also introduced a new concept.
Quick question.
Yeah, please.
Are you guys clear about what is the weights feature map? Maybe you can just give an example of a feature map and how you break it down compared to the weights, biases, activations.
Perfect. This is a very good question. So thank you for asking. So weights are the parameters of the neural network. Like if you, for example, have a transformer or convolution network, it's what you train your network on. So each layer will have, for example, a kernel, and the kernel will have parameters. These are the weights or the parameters of this node. So for example, what's the simplest network you can think about? ResNet. So you have a ResNet. Each layer will have a convolution with a kernel. So the parameters of the kernels are the weights. And they change while training, but while you are doing inference, they are typically static, read-only. So these are the network weights. You get the Onyx model or the PyTorch model, TensorFlow, whatever. You have the weights for each layer. And then you start running the network. This is the dynamic data. You push, for example, an image or a video stream. So this is the input feature map. It goes through your first layer. You have another output data. So this is your intermediate feature map between node 1 and node 0, and so on and so forth, until you get the final output feature map, which is the last data that the user will consume. So feature map are the dynamic data going through your network. And if you are talking about streaming processor, like ours, data flow, you don't push data and wait until it comes out. You keep feeding data. Data will go in, keep going through your network, and once the node 1 is free, it will consume more data and move forward. Does it answer your question?
Yes.
Perfect. Now, let's go here. Since we are talking about streaming, how these cores will communicate is a big deal as well. So you'll see a lot of papers talking about network on chip, and like you see also the approach of True North, and there are a lot of literature about this. Honestly, we decided to make it simple, and simplicity was the answer here. And I'll give you another famous startup approach as well. It's publicly available. So we decided to use reservoir concept between the producer and consumer. So it's data flow. Each node is a producer of data, feature map, and the next node is the consumer of the feature map. And as long as you have enough data, they will keep working concurrently. So the producer will produce data, but initially you don't have enough data for the consumer to start consuming. For example, let's use a conv layer. It might be a 3x3 kernel. So we need to produce at least 3 rows of feature map data for the consumer to start consuming. So when the pipeline is filling, you start filling the intermediate buffer, and the intermediate buffer is software defined. we have a software will define how large of a buffer needed for this producer and this consumer to keep them working concurrently. At some point, and this is the optimal that the compiler always aims for, producer and consumer will keep working concurrently. Producer will push data, consumer will read data without direct communication, which is a tricky part, but I'll not highlight it today. It's beyond this talk. And if you're not balancing them, you might overflow the buffer, not overflow, just reach the limit of the buffer, so the producer will stop producing until the consumer will consume, and this will add bubbles to your pipeline. Now, how this is handled, this is a different story about something called ILC. But also to give you a hint here, sometimes you have very high resolution networks, and the compiler will try to compile at the optimal point, and the producer consumer should always work together, but it won't have enough resources to compile. So the compiler is smart enough to go and say, okay, how about I reduce the buffer, but you have now like a domino logic effect. The producer will produce, and then it will fill the buffer, then the consumer will consume, and then you'll have the odd layers working, then the even layer working dynamically. You don't just tell this layer to work and not. So the compiler is trying to get the optimal performance, but if it cannot compile for the target resource, it will trade performance for survival in that case, or mappability. But this concept will require line of sight, if you'd say. It will require adjacency. So the producer and consumer need to share the same physical feature map buffer. Again, it's software defined. So the compiler will try to preserve adjacency whenever possible. But when it's not possible or it's not optimal, the compiler can create adjacency by inserting new nodes in the graph, which in that case, you can call it a bypass node. So this is happening during compilation time. And finally, it should be noted here that you still have data flow hazards, because you can have branch dependencies and you might end up with a deadlock in your network. So our compiler will do what we call flow simulation. And the flow simulation will decide the limits of the buffer, how large of a buffer need to be assigned to avoid any possible deadlock or data flow hazard. So now the data flow management is split between hardware that will manage the reservoir boundaries and equations in the compiler to also find the best reservoir boundaries for performance, and flow simulator to reiterate on the reservoir boundaries to avoid any data flow hazard. You don't want your network to deadlock under any condition. So this is the best balance we found. Now, it's publicly available. There are other data flow in the market. One of the famous data flow is Grok, and you can go to their videos. They also have smartphones. They build data flow, but their choice that they manage data flow purely software. So they do cycle accurate simulation for the network and insert wait cycles in the instructions to avoid data flow hazard and to avoid data corruption. This will require your compilation to be done in weeks. And it's good if you're using large language model that you deploy it on servers once, but for edge, it's very painful. If you need to have days and weeks for simulation to compile one model, it's not the best strategy. Now, again, that's best of my knowledge. According to their public data, maybe they are enhancing. We have this. And then for lighter weight models, we can compile and get you the optimal performance within minutes. So
pause here. The previous two, one more previous. One more slide. Yeah. So you can, I'm just explaining to the class.
Yeah, please.
You can think of you have a DNN or a CNN. So what Mohammed is showing is the hardware perspective. So the simple version that I'm giving you, he will give you a much better explanation, is that you have the layers in your network. You can think of the layers as just being mapped directly to the hardware compute elements. But now, so when you go from one layer to the next layer, you're passing on the data, right? So you have computed, it's gone through activation functions, it's going to the next layer. So that's actually happening directly one-to-one in hardware. So the next layer is the consumer. We need to keep this pipeline. In the beginning, the pipeline is empty. You fill it up. But after it's filled for the first time, then you need to keep this pipeline filled so that you have maximum throughput through the net. So as the network is flowing in your software model, in the hardware, we need to make sure that you have maximum throughput. And that's what he's showing with the buffer management that, and it depends on the type of model you use, what are the dimensions of the output and how do you balance that with the buffer. And the other aspect he was talking about is, okay, now the compiler knows what you're trying to do in software. The compiler has an idea of what are the hardware elements in terms of the RRAM and the SRAM. Then it has to figure out where to map, which elements, should I map, these different, the feature map should go where, which, essentially neurons should be mapped to which elements in hardware. But maybe Mohammed, you can give a slightly better refined thing.
No, actually, Rahul, you give a perfect explanation. Thank you so much. I really love it.
Yeah, because they only see the software side here. Yesterday, on Monday, we had a lecture on RRAM. So they have a little bit of idea of that. But now I'm trying to just expose them to your world, right? Yours is literally a whole world. Yeah, go ahead.
Thank you so much. And let me.
That's another question here.
May I add something quickly?
Yes.
So another thing also that, as Professor Mangaram mentioned, compiler is aware of that through tons of equations. We have a lot of equations to figure out what is the perfect buffer size based on the feature map size. Is it a math model? Is it like a conv layer? Is it just a bypass network? And then we have a full-fledged flow simulator to take it to the next level. So now it's a good time for the next question.
Is it possible for the consumer to consume the data from the buffer faster than the user can produce, such that the buffer becomes empty? If the buffer becomes empty, what would happen?
Sorry, can you repeat? I cannot hear it quite well.
If the consumer consumes data faster than the producer can produce it and the buffer becomes empty, what would happen in that case?
Oh, so the producer will stop producing. This is not an optimal case. It will introduce a bubble, but the hardware will survive it. So now the compiler should avoid this, should perfectly distribute the resources. But at some point, you will run out of resources. So either you have slower producer or faster consumer, because at the end, you have a unit, which is your core size. If to balance them, you need 3.5 cores, you cannot really have it. So there is a chance this will happen, but it will not, and that's why we are highlighting it here. It will not pose a data flow hazard because the hardware, the producer will automatically stop producing based on the ILC, which we'll not cover today, until you have enough for it to produce.
You optimize to the minimum buffer based on changes based on how did you figure out the default value of the
Sorry, I missed it again. Sorry, folks.
Yeah, so you mentioned the buffer minimum line, and how did you go about optimizing that?
Oh, yeah, this will take a whole lecture, folks. This is one of the major layers of our compiler, how to figure out the min and max of the buffer and the increment and decrement step. Let's assume now it's working, because going through it is very deep here. So the magic is happening, it's working, but there is a lot of equations and huge software behind it to enable it. So let me try to move a little bit faster. Now, our goal is efficiency. So now, and data reuse, as we mentioned, is a big part of it. Because at the end, neural networks or AI workload typically is bottlenecked by the memory bandwidth, even on-chip memory, even with distributed memories. Doesn't matter, you will hit your memory bandwidth at some point if your cores are efficient enough. So also the compiler is aware of how many cores assigned to each layer. It has an architectural model, equation-based model in the compiler. It's aware like this layer, I need to assign it 4 cores for optimal performance. By the way, just a hint here, folks, mapping in this case is an NP-hard problem. It's an optimization. There is not like an analytical solution for it. So it tries its best through the optimizer, through different optimization techniques to assign the right number of cores for each layer and place and route them in the perfect scenario. But there's also another question, how these cores work, how these cores are working together. So you assign 4 cores for, in that case, let's consider it a convolution layer for simplest. So what we are showing here is the data planes. Like you have a feature map with X, Y, and channels dimension. How do you distribute the workload among the cores? So one possible, which we call it output channel distribution, each core will compute one of the channel planes. And another one, which we call it pixel worker, each core will compute subset of the pixels and all the channel planes. And there are more. I'm here just highlighting a couple of them. So which one is better? Each one has its own pros and cons. Each one is better for a given layer and better for a given optimization point. For example, pixel workers will increase the weight memory reuse significantly, because since all of them are computing through the whole plane, they can reuse the weight memory from each other. So adjacent cores can share the weight memory fetched data together. But it has a limitation, maybe for matmul layers or dense layers, because you need enough pixels to speed up. So in that case, output channel can actually work on the channel plane. And I'll give you an ancient example. ImageNet. ImageNet, the last layer will have 1,000 classes, but 1 pixel. So you cannot really optimize it based on pixel workers, but you can optimize it based on channels. And there are a lot. And then the compiler, during the compilation, knows how many cores for each node. So I'll just go backward a little bit. So now we start seeing how this is happening. Node 0 is becoming 4 cores. Why? Because the compiler, through the optimizer, figured out that 4 cores are the best number of cores to assign to cores node 0. And also it figured out that node 0 should work as pixel workers or compound or channel first or whatever, and then it assign it. Once it's compiled, you deploy to the chip and it will keep working like this. You push data in, you get data out. So moving a little bit faster.
I just want to mention that, so all this, Mohammed has actually documented this in detail in the developer.MemryX. If you go to architectural overview,
Yeah.
all this, so this is quite a lot for you all to absorb, but you can see that in detail. This is really important to know, how does your model actually map to hardware? This is not one human world anymore. Go ahead.
And that's why, to be honest, Rahul, initially I had the software first, but the software is good and everything. But I want people to know that to enable efficient AI, there are a lot of hardware innovation enabling it. Maybe our customers or users in the market, they don't see this. They just see an efficient chip, plug and play models. But from an academic perspective, this is what enables it. So as the professor mentioned, there is a white paper detailing this. I'm sorry if I overwhelm you for information.
No.
Yeah.
I'm just giving them more information where to
Yeah.
look for. If 1% of the class is interested, then they can check.
Definitely. And this is my last slide about the architecture. We just scratch the surface here. Another thing is hybrid precision. So like, what kind of precision should you use? A lot of initial chips, people were using End4 and End8 for weights and activations. For weights, it does make sense. For activation, it ended up that, okay, but I now need to tune my fixed point range. And guys, this is a little bit involved, so I'll just mention it and we'll move forward after it. Usually, if you're an End8 or End4 activation, the it's fixed point. It's not really end. So where you put the point of your decimal point depends on your nature of your dynamic data. So usually people will tune the chip using pilot images, and it will be very sensitive in the run condition. If you're deploying it in a field, we have customer information that people using Int8, sometimes they lose up to third or more of the accuracy. Like your accuracy is claimed in the lab control environment to be, for example, 50 for MAP, but in the field with different dynamic data, you get much lower. But if you use floating point activations, you are not efficient anymore. So what we introduced, and now there are a lot of similar in the literature, but we introduced a long time ago, is what we call here group P float, and it's now better known as block float, is we shared the exponent among several mantises for activations. So it's the best of two worlds. It has the dynamic range, and this shared exponent will work very well for neural network and AI workload. And it's from a hardware perspective as efficient as an Int8. So this also, another thing you consider, are you chasing just benchmark, or you need your chip to be usable at the end? If you're just chasing benchmark, if you use Int4 versus Int4, you'll claim I have this amazing TOPS per watt, but people will not use it in the market because it will be terrible. Then you need also to balance this. Could we get higher FPS per watt for our chips? Yeah, but we'll make it less usable. It's very high while achieving the usability as well. And also achieving efficient max is a big deal. Max is the heart of the accelerator. So this is the
Just one second. So one thing we did in class was just do the quantization down to Int8.
Yeah.
But in production, you would actually have mixed precision models.
Yes.
So even the layers would have different precisions along with that. So you would train with high precision, but the inference could be mixed precision, right? So this hybrid precision is saying, okay, we support that, but we have a very efficient way of even encoding, that's exponential.
Definitely. And our weights are Int8 or Int4 or Int16. And usually it could be hybrid precision. For smarter users and customers, we offer them a way to define the precision per layer, not per model. But our activations, in that case, we always go for that hybrid approach of group P float. And now if you are training your network for 4-bit and you need TinyML, just one chip, it will be definitely supported. Okay, I don't know how much time I do have. Like, do I have 10 minutes, 5 minutes?
Yeah, 10 minutes is good. Don't need
Sorry?
to. Yeah, 10 minutes is good.
Okay, so I'll try to move a little bit faster in the software. Now we have a good hardware, at least that's what we claim. It's very efficient, but without a very strong software layer, it will not fly. And let me tell you something, the MemryX team spent 10x of the time on the software compared to the hardware, literally. So you need, our approach is offline compile. We don't want people to prune or tune the models. You can definitely do it if you want. If you need to run tiny models, TinyML, it's very advisable, but we are not relying on it. So you can get any model, whatever your framework, you compile it through the compiler offline, you get what we call DFP, data flow program. And the DFP is telling, DFP is this. Telling each core what you will do, how many cores, how they will communicate. It's capturing all the architectural software-defined concept here. And you get this DFP, you deploy it to the accelerator, and that's it. You push data in, you get data out. Streaming, you can do this forever. And it's very power efficient. If you don't have data, the cores will go. No data, sleep. It's not like control flow. They are always fetching. If you don't have data, they will go autonomously in very low power mode, and the power of the chip will go definitely down. And then you can actually have multiple models concurrently, and you can push multiple streams because, again, it's data flow. It's really true parallel. It's not like you are context switching between two workloads. They are running literally in parallel because you'll have subset of the cores connected for the first model and subset for the second. And how this happening?
Also, so I just,
Yes,
so I did like some very lightweight benchmarking back in 22, 23 for this MemryX, the earlier version of this chip.
Yeah.
We could take like these models of, autonomous driving cars, all like 8 cameras that are around the cars, feed that in directly to this chip. And like say a Raspberry Pi just collects the data, but then this acts as the main processor. It can process all of them in parallel. You can feed it the LiDAR data as what he's showing as the yellow thing, that's the camera, 8 camera streams. This is LiDAR, radar going in. It can process all of that and it's flowing through, at line speed. That means as it's getting produced in real time. Yeah, go ahead.
Thank you so much for the hint and the insight. As Professor Mangaram mentioned, it's just you push data in, connect data out, collect data out. So what you need is runtime APIs to push data and collect data, and you build your user app around it. And I can show you a couple of examples quickly. You can have, for example, one model data flow. Of course, no one will go in production with one model. So usually if you have a depth model, simplest model here, you capture the data. Maybe it's camera in that case, maybe it's OpenCV. You pre-process your data because your model is trained on like maybe from 0 to 1, but your data coming from the camera is from 0 to 255, for example. You downstream the cam to the model resolution. And then you run the depth model, and then you have metadata. You have to post-process it to get actual useful data for your user. You might display it or control a robot or whatever. And in our case, you have the DFP, everything heavy lifting is running on the accelerator, and you have an input function and an output function that wrap your capture and pre-processing and post-processing. You might have more complex pipelines, like if you have an object detector, you need to overlay the initial frame, so you might need a frame queue to overlay it. You might have like more innovative pipelines. Like here, 2 models are co-mapped into the accelerator. One is face detection. This is simple, but you can go as complex as possible. And one is face recognition. They can run fully in parallel. If you detect a face, you run the face recognition once. If you don't detect, you'll not run it. And if you detect multiple faces, you run the face recognition multiple times while still streaming the next frame. And then they can co-map. And for this one is like, it's a bit ancient now, but it's a good example. The MediaPipe holistic model by Google. It has 5 models. One of them will detect the person, and then if it detects the person, it will do the landmarks for the person, and then will crop the face and hands more accurately and do more accurate landmarks for the face and the hands. And in that case, we can co-compile all the models to our M.2 module. But what if you have 40 models use case? Some companies we are collaborating with, I have face detector and they have license face detector and they have vehicle detector. It depends on the scenario, what's happening in front of the cam. It's fine. You can actually create multiple DFPs and the software will manage the swapping under the hood, given the target latency fully transparent to the user. And then you add more layers on top of it. The model is one thing, but in production, you need object tracking, temporal smoothing, ROI focusing. You can't. The accuracy of a YOLO model, for example, is 50 MAP, but in a production, people accept 99.9 accuracy. MAP and accuracy is not the same. No false positive, no false negative. You take it by the other software layers. And we have a lot of technical examples.
Mohammed, that question for the previous slide. So, I mean, do some of these have like, single-threaded processing that they have to do and interleave it with, say, like you're running your model in parallel, then you have to do some single-threaded processing for some logic.
Yeah.
And then how do you switch back and forth between the single-threaded processing and the parallel processing?
So the model will run in parallel. If you really are purely single threaded, it will introduce here some bottleneck. because in that case, you cannot push data and process the intermediate data. So you need some multi-threaded. So we offered our users two ways. We offered them, so this is recent APIs like introduced last year. We offered them actual multi-threaded, but a lot of people complained about, I don't want to write my program multi-threaded. I don't want to change my code. So actual multi-threaded will handle it, but we also offer asynchronous programming that you actually don't care about threading, will control threading under the hood. You have functions that are written sequentially in your code, but they will run parallel under the hood through our runtime. So in that case, you write a sequential program as if it's single-threaded. You have an input function to feed the data, another function to process the intermediate data, a third function to process the output data, written in a single-threaded fashion. So you don't write multi-threaded program, and under the hood, our runtime will do all the multi-threading for you, so it will not pose a bottleneck. So we offer all the options, and if someone wants strictly to run multi-threaded to keep the CPU very lightweight, they can also do this. And this is part of the software layers here, Rahul. You pull something, it's perfectly fine for one use case, but when you go and talk to VMS, go to talk to drone folks, you go to talk, everyone will have different requirements, and you need to expand your software layer. So it's kind of inverse pyramid here.
Right.
Thank you so much. And we have a lot of technical examples. Feel free to check them. I know that I had only 10 minutes. I have 1 minute left. So let me show you, if you have a second. So feel free to visit our developer hub. Which one will be easier on your screen? I think the white is better. We have everything, and you can have the tools to compile a model. In our case, you just download a model, compile it, and deploy it. That's it. And then build your application around it. We have what we call Model Explorer. It's not a model zoo. Of course, smart folks like you will tune and optimize the models, but it's not required. Here we have a tool that will go and scrape the internet, download hundreds of models. In turn, we have thousands of models auto-downloaded, compiled, auto-benchmarked on our hardware. We don't expose all the sources because some of them are not as reliable. We only expose reliable sources. So we have here all these models, like on the current point of time, 450 models, and they are keep expanding. None of, like a little bit, we optimize a couple because customers ask it for it. Using group pruning or whatever, but we are tagging the optimized ones. But you can go for any use case and download the model as is, compile it. Maybe other competition will only rely on a model zoo that only optimized models are presented. We are very proud of our software and hardware that even out of the box models are offering huge performance. And people invest a lot in training their models, and we need to be faithful to it. And then we have, of course, the tools, documentation can go through it. We have a lot of tutorials taking people from very basic steps to like advanced use cases. We have, as the professor mentioned, the architecture overview document. You can go through it with a lot of details about what we covered today, more in depth. And finally, if you're interested, you can have end-to-end examples that showing you technical use cases. We don't have the production deployment or production ready here. We have only the technical examples. That's also going like simple depth estimation. You can take it to the next level and do a point cloud analysis, or open vocabulary like YOLO-E that you can run any query, satellite image, like even some of the team members build some games. Fantastic. So I'll stop here. Today, we went through the MemryX and its product, very high level concept of the data flow architecture to tell you what's under the hood, and quickly cover the software stack and explore the developer hub. So thank you so much for the kind invitation. And if any questions, and if we still have time, I can answer them.
Let's give Mohammed.
Thank you.
And I think you guys were recently very well funded, and I told the class if there are good competent students, they you'll consider their resumes.
Oh, yeah, sorry, I missed this part. I should have added the QR code, sorry. We are always looking for talented folks like you. So on our MemryX page, there is the hiring page. At Anarpur, I have 2 or 3 job openings. You might not have internship written especially, but even if you are applying for internship, just add it to the cover letter. We are always looking for talented folks to join our team.
Thank you so much, Mom. Any, I know we had a lot of questions during your talk. Any other questions? Okay, great. Thank you so much, Mohammed. This was actually really amazing.
Thank you so
I
much.
learned a lot myself from your talk, and I think this is just, sort of just grazing the surface of how much, goes into making a next generation chip. This is not Intel or NVIDIA This is a complete rethinking, but it's also like, doing a PhD, writing many papers, best papers, and then following that, making a company, then actually having the reality hit you that, just the research alone is not sufficient. You have to then work with, chip design vendors, work with foundries, get the production going, and do all of the software side of things, right? So I think, and so if someone like Mohammed, if you think of yourself, 10, 15 years in the future, this is like he has a Swiss Army knife of skills that he has developed over the years, but with a lot of foundations, right? You can't just jump unfortunately with a bachelor's today, but you have to choose wisely. He chose very wisely on the path that he wanted, but you have to be bold and have guts too. Thanks a lot, Mohammed. Very nice.
Thank you so much, and thank you so much for the kind conclusion. It was a pleasure being with you and your students today.
Thank you so much.
Thank you. Yeah, bye.
Thank you.